to introduce our speaker. So Dr. Zwemer is the president of Intercax LLC out of Atlanta, Georgia. The company supplies model-based systems engineering software platforms, and a couple of those are listed down at the bottom here. Dr. Zwemer is an active instructor, teacher, and consultant in the field, and very impressively holds a level 4 model builder from the advanced certification of the Object Management Group System Modeling Professional. So we're really excited to have him to talk tonight on building digital threads. Can't wait to hear what he has to offer. And with that, I will introduce Dr. Zwemer. And Dr. Zwemer, I'm going to stop sharing here and let you, there we go, let you share the screen.
Thank you very much, Steve. I appreciate the introduction. I appreciate the invitation from the chapter, and especially from Rosemary Kyoko, who originally extended the invitation. She and I have worked on SysML training, among other topics, over the last couple of years, and I'm very pleased to be here tonight. As I was telling some of the early arrivals, I've actually spent a lot of time out on the Eastern Shore, not too far from Annapolis. I think my parents moved there about 30 years ago. It's a beautiful part of the country. I'm only kind of sorry I'm doing it remotely this time. But let me go ahead and get started. I'm going to suggest that we hold the questions till the end. I'll try to make sure we have plenty of time for any questions that come up, but that way I can kind of get through the material I'd like to present tonight without too much delay. So just to start off again, my name is Dirk Zwemer. I'm the president of Intercax and one of the co-founders. If you're not familiar with our company, we've been around since about 2008. Our primary center is in Atlanta, Georgia. We have some additional staff in India and Germany. And our business is entirely about creating software for model-based systems engineering. An important part of my job, and a part that I particularly enjoy, is to work with organizations that are new to model-based digital engineering and help them understand what that is and how our product offerings at Intercax can help them move forward in that area. So this evening I wanted to talk about digital threads. You've probably heard and read a lot about digital threads recently and how they're going to do wonderful things for systems engineering. But what I want to do is focus on an aspect of the topic that hasn't received as much coverage as some others. That is the practical issues of building a digital thread, of making the connections that form the digital thread. And I don't mean this to be a commercial for our product, Syndeia, but I am going to use screenshots and videos from it for my examples to emphasize that the digital thread is not just some theoretical concept, but something that you can build and use today, whatever vendor platform you might choose. So you probably wouldn't be here if you didn't understand the grand problem. Organizations developing complex systems use a wide variety of engineering models and data repositories. That makes it hard for individual team members to find the information they need to do their jobs. Engineers spend an inordinate amount of time searching for, transcribing, updating, and verifying existing information, time that they're not using for real engineering. Collating the data for review and project deliverables is slow. We don't recognize errors and missing pieces until late in the game, so projects run late and over budget. Well, you may have been told that the solution is the digital thread. So what is that? Many people have tried to define it. Certain key phrases here leaped out. Linked set of digital artifacts, connected data flows, actively managed, integrated view. These are all phrases that get us closer to an idea. And other definitions suggest that the digital thread is the way in which we do our work, like the use of digital tools, communications framework, a data-driven architecture. These all focus on process rather than what we produce. So for this talk, what I want to say is that the digital thread looks something like this. Rather than trying to bring all of the information about the system into a single database or a data lake, we leave the information in the individual models in which it is created and used, and we federate it, tying it together into a single unified whole. So each of the circles in this diagram represents a different model of a different aspect of the system. Within each model, there are model elements, artifacts like requirements and behaviors and simulation results. And within that individual model, these are connected together. We're going to call those intra-model connections, intra for inside the model. But we also want to tie these separate models together, and that's what the dashed orange lines represent. We're going to call those inter-model relations, inter for between models. So one of the purposes of Syndea is to create and manage these inter-model relations. So we have both the intra-model relations that are maintained by the separate repositories, and we have the inter-model relations that are maintained by some kind of a digital thread platform. Now, I tend to refer to this entire network that we've created as the digital thread. And some of my colleagues who are more precise say that a digital thread is a specific path across a network. So one of these dashed red lines traced all the way across. And that the collection of all of these threads form a digital fabric or a digital tapestry. But, I think you get the idea of what we're talking about here. And so then that leads us to a proposed architecture for a digital thread platform. It is an intermediary between your data sources, all those engineering model repositories that you use, and your data consumers, the many interfaces or user experiences your team needs to access, analyze, and manipulate the data. So this digital thread platform needs to do three things. First, it needs the capability to explore disorganized data to discover what ought to be part of the digital thread. Essentially, we're looking down from the data consumer level down into the data within the individual repositories, even before it's connected. Next, you want the curation of a set of these digital threads, that is, creation for the creation, reporting, update, and deletion of these digital threads. That is, you need a way of tying together data elements within these repositories into the digital thread. And then finally, you want visualization and analytics over the digital threads and to the underlying connected digital artifacts. That is, you want to be able to extract the information out of these repositories and bring it up in an organized and useful fashion to your data consumers. Well, if you can do that, you can do a lot of really cool stuff. You can interactively trace connections across the digital thread. So here's a following of a particular digital thread as a set of visualized elements. You can query the digital thread as a graph, and you can extract patterns and anti-patterns. You can extract critical metrics about the project that you're working on. Things about the size, completeness, consistency, and concurrency of a particular systems engineering project. Or you can track project activity over time. Here's the creation of relations within the digital thread for different repositories tracked over time. But I'm not going to talk about that tonight, because before you can query and analyze and visualize the digital thread, you have to build it. And so that's what I want to talk about. So I'm going to talk about 5, okay. I will also mention that in the case of our product offering, Syndea, if you get an annual subscription license, it provides a network-based set of microservices called Syndea Cloud that's hosted on your network or your private cloud. And essentially, these services are embedded in your development environment to be able to do those things we're talking about, to read and write the contents of the underlying repositories, to be able to create that network of intermodal connections, to provide the visualization and the analytics, and to do it all with security. That is, to make sure you're authenticating users' access to the specific data sources. And those services all are available through an open, fully documented API, a REST-based API following the HTTPS standards, so that all of these services are available through the API. And then we also provide a set of specialized clients that support particular use cases, and you'll see examples of some of those tonight. Ways of being able to exercise those services to do useful things. And as I said, the focus of the useful things tonight is actually building the digital thread. So I'm going to talk about 5 ways that I could use such services to be able to build a digital thread. The first is manually linking pre-existing data elements across model boundaries. Then we're going to talk about being able to create linkages by transforming data between model repositories, moving data and creating the digital thread at the same time. And then we're going to start to take some of those ideas and we're going to try to make them easier to use, more automated. We're going to talk about using key parameter matches to be able to link data elements automatically. We'll start to talk about rule-based reasoning and automation of building the digital thread. And we'll talk even a little bit at the end about artificial intelligence, how we can use machine learning in combination with automation to build the digital thread. So at Intercax, we're actually pursuing all of these. They all have their different use cases. And basically, as a community, we're all still learning what works and what doesn't. So it's kind of early to trim out all of the options. Okay. So let's start with the first of these approaches, that is manually linking pre-existing data elements. Now, in our world, we call these reference connections. If I have a SysML block and a JIRA issue, I can simply create a reference connection between the two of them. Or I can create a reference connection from the SysML block to a file in GitHub. Or I could connect that file in GitHub directly to the JIRA issue. These are all types of reference connections. And a digital thread platform has to be able to keep track of them. So what I'm going to do now is show a short video where we're going to be able to create some reference connections, through the Syndea web dashboard to start building a digital thread. So let's see if that comes through all right. I should be able to show a short video here. Hopefully this is coming through. I hope somebody will speak up if it's not. But we'll start the video here. This is the Syndea web dashboard. That is one of the clients that Syndea can use. And what we're doing is dragging a component, in this case, I'm sorry, I think I've skipped forward here. sometimes these video playbacks. This is the Syndea web dashboard. We're actually looking at the contents of a GitHub repository via the Syndea Cloud REST API. And we can also look at the contents of other repositories. This is a test rail repository. What I basically want to show here is that we are using the Syndea Cloud as an intermediary to allow us to look at the individual data within two different repositories, GitHub and TestRail. And now we're going to start linking them together. This is, again, part of the Syndea web dashboard. I'm going to pick a set of elements from the GitHub repository on the left side here and drill down into it. And on the right side, I'm going to do some similar things with the TestRail repository. These are both online data repositories. Syndea is reaching out to those repositories, as we expand these and looking at the contents of them, and we can see the contents of both repositories in this same interface. And we're simply going to start creating linkages, in this case, between test cases on the right side and software files on the left, presumed to be linked together. And in this particular mechanism, we're simply checking a box on each side and clicking a button that says create a reference connection, and we've just created a first reference connection. I'm going to pick two different boxes, two different objects, and create a linkage between them. And so, we can go through the process to be able to build that kind of a digital thread between them. Each time we do this, we're adding an additional linkage, if you like, a digital stitch to the mode. If we go back and look at a particular element in one of those, we can ask, okay, what is it connected to? And we can even look at that over on the right side here. We see all the connections to this particular object within the Syndea database. And one other thing here, which is a little hard to see, is that there's this parameter called exact version. What we're doing here is keeping track of which version of the element we're connected to. In other words, are we connected to the latest version of that element with the connection that we've created? Or has that element changed since the connection was created? And we now need to be able to detect that there's a later version and that we have to update our model to include the latest version within the digital thread. So all of this information, in this case, is through a web browser. But the important thing about reference connections is that they provide traceability between model elements in different models. They don't move information, but they can provide you access to that information quickly across the connection. And they can also check for changes across that connection, as I said. So if I have a particular SysML block connected to a Jira issue, I can use that connection to find out whether the Jira issue has changed. Am I connected to an old version of that Jira issue? Is there a newer version of that Jira issue? So my digital thread platform needs to be able to tell me that. And if I want to be able to repoint the connection to the latest version of that Jira issue, I want to be able to update the connection. So that's what we call a reference connection. This is probably the simplest way to build the digital thread, but it's pretty obvious that fatigue could set in quickly, and the chances of operator error increases. So let's talk about the steps to building a digital thread. I'll go back to the slides here, move forward. Probably a more efficient way to create connections is by model transform, where we can take model elements in one tool and then bring them into a second tool to create a new set of model elements. And the model elements in both tools remain connected. So we're doing two things. First, we're moving information by creating a new set of model elements in the second tool. And second, we're connecting those new elements back to the original elements and keeping them connected. because they're connected, we can compare them as we go forward, as one or both of the models change, and we can detect how they've changed. So this is an example of that. You have a CAD model, this complex assembly model, and we're going to drag that into a SysML modeling tool and create a block structure with parts and attributes from the CAD model. And each of these parts is connected back to the CAD model. So a whole set of connections is created in a single action. Again, let's go back, take a look at a short video which shows model transforms from Vitek Genesis to Windchill and to JAMA. All right, so again, if we choose here, this is a different interface. This happens to be a client which allows us to put, in this case, the Genesis model on the left side and the Windchill model on the right side. And we're going to use a simple drag and drop to be able to take components from the Genesis model and drag them into Windchill. And then later we'll do something similar with top-level requirements from Genesis into JAMA. So let's just kind of follow that process here. I'm simply taking a high-level element here and dragging it into an empty package in a Windchill repository. And what we're going to do within Windchill now is create a bill of materials within Windchill that reflects the SysML structure. And we can go and we can actually go into Windchill and we can see the bill of materials that's just been created from the Genesis model. So again, we've created not only a single connection here, we've created a large number of connections because each of these parts in Windchill is connected back to the original component in Genesis to be able to do that. And again, we have this set of connections that's been created, a multi-level bill of materials in Windchill from the SysML model. And that was done with a single drag and drop of the top level. And now on the right side, we're going to go to a requirements repository. And we're going to do something similar. We're going to pick a high-level requirement, which has multiple layers of sub-requirements from Genesis. And in this case, we're simply making connection by doing a drag and drop into an empty project on the JAMA side, with again the same result, is that we are creating a hierarchy of requirements in JAMA that are the same as the requirements that start out of Genesis. And we again have the ability to go into JAMA and see those requirements that we've just created. And again, if we want to start to do here, we can compare attribute values. We can do updating as well. And in the process of doing this, those two actions have created 37 different connections between those three tools in terms of the process. So again, we've used, in this case, drag and drop to create connections, but by dragging top-level components from Genesis into these other models, we've not only created new models in those repositories, we've added 37 relations to the digital thread in simply 2 actions. So that's a much more efficient way to be able to create new connections to build a digital thread than the single stitching one by one. And those connections give us a way to compare and update information across those connections going forward. And this is only one example of a kind of model transformation that might actually be useful. And we've looked at requirements in architecture. We've looked at architecture in PLM, architecture in CAD. Architecture in simulation is quite interesting. We could do something very similar with Simulink. So again, I can go and I can do a quick video to show what happens if we have a model in this case, Cameo, and we want to be able to bring it into Simulink. So just go ahead to the next short video. And what we're starting here within Simulink is a set of internal block diagrams, essentially connectivity within the SysML model. It's a multi-layer model. Each of these elements can have inner elements as well. And we can take this entire set of connections, this entire set of IBDs, and we can drag this into Simulink. And again, here's the interface here. We've got SysML on the left side. In this case, we've simply got an empty package on our local system, and we're going to drag the top level element from the SysML model, that is the payload element, and we're going to drag it into my local package. We're going to say I want to create a Simulink model out of that, and then that process is going to go forward. And within Simulink, you're going to build this. Now we can open MATLAB and we can look at that Simulink model. All of the connections have been carried over. All of the blocks, ports, and connectors from SysML have been carried into Simulink. And each one of those blocks in Simulink is connected back to the original block in the SysML model. And we can do a little rearranging of the diagrams, but essentially all of that structural information has been carried over in a single transaction, and a whole series of connections for each of the blocks has been carried over as well. So again, this kind of model transformation is a relatively efficient way to build a lot of connections into your digital thread in a single action. All right. So by doing this kind of model transform, you also have the ability to, again, compare the two models as you go forward in time. If one side or the other changes, our digital thread platform needs to let us see that. And it even may give us the ability to update the Simulink model with the latest version of the SysML model, or vice versa, because we can do a Simulink to SysML model transform in the opposite direction equally well. All right, so that really covers the first of the two ways that I wanted to talk about building a digital thread. Now we'll move on to the third. We have seen that model transforms can create some connections in our digital thread more efficiently than creating reference links, a single connection at a time. But even so, they still require manual action. They're prone to operator error and maybe operator tedium. We really do want to look for more efficient approaches. So as a kind of a first step in this direction, we added some utilities to Syndea to be able to create connections based on key parameter matches between data elements. And this is a form-based setup. Here's an example of such a dashboard for one of these utilities. So the first thing it does is it identifies a set of elements in two different repositories. In this case, we have a SysML model from Cameo in this case on the left side, and a JAMA model, requirements model on the right side. So that's the first step, was we have to decide the scope of the two models where we're going to be looking for matches. The next is that you want to look for the type of elements on each side where matches will be considered. And in this case, that's a requirement on the SysML side and a requirement on the JAMA side. And then you have to identify what is the key attributes that have to match in order for the connections to be created. So in this case that we're saying there has to be an ID on the SysML side that matches an ID on the JAMA side. And if those things do match, then your platform is able to find what elements actually do match. So these are the SysML side elements. These are the JAMA side elements. Our particular utility is found that they have matching IDs. And so we've decided to select all of them. And then we will finally generate new connections between them. Now, when we do generate these connections, there's an additional piece of information we have to provide, which is how we want them connected, how we want them to map into each other. If they have shared attributes, how do we want those attributes to be linked, or whether we want those attributes to be linked? So part of what we have down here at the bottom of this particular utility is a way of being able to choose how we want the connection to be created, what mapping between these two domains we want to choose. One of the things that this particular digital thread platform provides is a way to create your own custom mappings. So the users can create the mappings. They're not confined to whatever Intercax has created. So this is another way to start to kind of automate the process. But it's still a relatively inflexible way to go ahead and automate the creation of new matches. Among other things, there seem to be relatively few cases where there is an exact attribute match between two different model repositories. So we really need a more flexible approach to express and execute rule-based listening in order to create connections and build the digital thread. Well, fortunately, Syndea is an API-first platform. What that means is that all of its functionality is available through a fully documented open REST API, so that all of the endpoints are available not just for Syndea itself, but for the underlying repositories. That means we can create custom scripts to be able to examine the digital thread, identify new connections to be made, and to generate reports of the information from the digital thread. Well, one way in which we do this, an easy way to do this, is to use a popular data science application, the Jupyter Notebook. A Jupyter Notebook is an open source notebook type environment where we can run down, or where we can write down queries, and then we can look at the results of those queries that are returned by the digital thread platform and format them as tables and graphs. So if you can create one of these notebooks, and then you can run it. You can run it at any time, and it'll call the digital thread for the latest information. The goal that we have here is sometimes called seamless integration or seamless traceability. The idea is that the connections are created automatically in the background based on some time trigger or event trigger without requiring human intention. So this reduces human effort and the possibility of human error, and kind of allows the digital thread to grow on its own as a natural byproduct of the development effort. I think you call it kind of seamless because of the sense that nothing can fall through the cracks. You're not relying on the human engineer to remember to update the digital thread, to add the new components into the digital thread. All of this happens in the background according to some rules that you've built into these scripts. As I said, we like to use Jupyter Notebooks for this for our own work. With the Syndea 3.5 release, we actually provide a number of different sample notebooks. So not only do you get the sample code, they basically allow the user to modify and test changes on the fly. So what I want to do here is look at another short video. And it's really designed, this particular video, to find all of the JAMA requirements under a specific top-level requirement and to create a JIRA issue for each, and with a connection back to the JAMA requirement source. So again, let's go back to that right now. Again, what we're looking at here is the running of a Jupyter notebook. It's an interactive cell-based notebook format. Let's go ahead and get this particular started. The initial cells are focused very much on being able to log into the REST API of Syndeia Cloud. And I have, through the documentation with the REST API, all of the different methods, all of the different endpoints that allow me to access information, not only from Syndeia about the intermodel connections, but all of the information from the individual repositories like JAMA or Teamwork Cloud. And I'm going to use those endpoints that are available to log into Syndeia Cloud through the notebook itself, then to be able to start to ask questions of the digital thread within the notebook itself. And that's going to start by logging into JAMA Connect, that is the JAMA repository. I'm going to look for requirements that meet certain prerequisites within JAMA and get a list of the different requirements. And then I'm going to take each one of those requirements and I'm going to generate a task in JIRA that is linked back to that requirement. And then after I've run this particular Jupyter notebook, then I will have a new set of JIRA tasks, this is the final list here, that have been created from the JAMA requirements that were within the scope of this particular exercise. And so this is an automated thing. It can run all the way through by itself. Anytime, I want, I could run this. It will look at that same scope of requirements. If there are any new ones in the list now, it will create new JIRA tasks that correspond to them and that are connected back to them. So again, this idea of the automated creation of these connections, maybe you have this particular notebook or this particular script being run, once a day, middle of the night, the next morning, the workers come in, the engineers come in, and they found that their digital thread has been updated overnight so that the new requirements that have been created yesterday are now linked to new JIRA tasks that are available within the system. All right, so probably took me a couple of hours to build and to debug this particular notebook. And now I want to be able to set it up and run it automatically. So in this particular case, what we want to do is to be able to create automated workflows, which in our business are often called digital pipelines. So a series of steps that will call our digital thread platform, take a set of actions, get the information we need, and present it in the way we want. So, conceptually, a digital pipeline is a series of tasks. And then we can use very common DevOps tools from the software engineering world, like Jenkins or GitHub Actions. And we can use those to trigger this script at some regular interval. And each time you run this particular report, for example, a series of updates, the running of that particular script can be preserved as a history of the system model. So again, I've got a whole series of runs of this particular thing. I think we have a moment to actually look at an additional video to show what this actually looks like one way that we've set this particular up. Here we are working within the GitHub world. We've got a particular notebook, one of the notebooks we've just created. We've set up our DevOps pipelines that every time I modify this particular notebook, and that's what I'm doing in GitHub right now, I'm changing the date on it and commit that change, it is automatically run along with a series of other notebooks. And then copies of those completed notebooks are stored in GitHub in a different repository with a timestamp on them, so that I can see what the result of the running of that script at that time was. Again, I can set it up to run every morning, every afternoon. Here's the list of all of the runs that we've completed. I could view them in GitHub, but I can also view them in other tools. This is called Notebook Viewer. It's just a way of looking at a Jupyter notebook in a web browser. Even if you don't have GitHub, it gives you a chance to go in and look at the latest version of the latest run of this, so that all of the information that was created in this particular run, all of the new connections that were created, can be observed. So again, in this case, we've used a digital pipeline. It's set up using GitHub Actions. Whenever I've uploaded that new notebook, all of the notebooks in that folder are run automatically. So by doing this now, we can have the creation of the digital thread going up in the background, essentially. It's being built in the background following a particular set of rules. Again, the goal that we've had in this area has been to make the capabilities of the digital thread platform available to all kinds of different analytics and DevOps tools, not just to provide our own interface, our own restrictive user experiences. But if we want to, we can create, more dedicated applications. This was a demo we built recently to show how you might set up an updating from JAMA to Windchill. Again, for each requirement that you have in JAMA, I want to create a connection to a part in Windchill. And in this particular case, we're not going to create the connection automatically. We're not going to create a new Windchill part automatically. But what we can create is an engineering change notice on the Windchill side. So again, what we're respecting is a particular organization's workflow in something like this. Again, it's using the capabilities of the digital thread platform being run through a standard automation service. But again, it allows us to look at a particular tool. In this case, we're looking at the contents of a particular project in JAMA Connect, and be able to recognize if new requirements have been added or old requirements have been updated. And for each example of that we found, we are going to go into PTC Windchill and create an engineering change notice, so that the worker on the engineer on the PTC Windchill side is going to have a notice that something on the JAMA side has changed, and then they will be able to act and decide whether that requires a change on the Windchill side. So again, all of this capability is something that you want to have in your digital thread platform, so that these type of building of the digital thread can proceed without human intervention. So once the queries and the algorithms have been developed, and you might have tested them in an interactive mode like the Jupyter Notebook, it becomes easy to program a custom behind-the-scenes execution engine that runs periodically to update the digital thread. So in this example, we've demonstrated that kind of a seamless integration between Java Connect and Windchill, where we can add or update elements on either side, and they're mirrored on the other side as soon as the Syndea automation services run. It also can include things like adding comments with links into the requirement, into the part that reference the other side of the connection. But we can build these automated digital thread creations so that they respect the workflow that this particular tool or set of tools requires. All right. So, this kind of custom scripting, really does seem like a better way to build a digital thread. But it still requires somebody to write the rules and to formulate the pattern matching algorithms for the scripts. Really the new frontier in this area, and this is the last of the methods for building the digital thread that I wanted to talk about, is it uses machine learning and artificial intelligence to be able to detect graph patterns and rules based on existing digital threads. So like a lot of different areas right now, artificial intelligence and machine learning is going to have a big impact on systems engineering. Now, I don't have any working examples to share yet, but the concept that we're working on looks something like this. If we start from this step I1 here, in this particular slide, this digital thread platform provides machine learning algorithms that mine existing digital threads and their artifacts in various model repositories and their inter and intra-model relationships. And it uses that to predict graph patterns and anti-patterns that we can use to build and validate new or to update existing digital threads. So again, the idea is that we take an existing digital thread, we apply machine learning to discover the kinds of connections that are desirable, that are characteristic of this. And as those patterns are developed, the algorithms for detecting those kinds of patterns are developed, you can then bring a human into the loop to review those new graph patterns and add, anti-patterns. And they become accepted patterns, accepted algorithms for automation. For, example, the machine learning algorithms might predict, based on existing data, that hardware requirements can be traced to part designs in PLM CAD systems, to manufacturing data for the parts in ERP systems, and to quality inspection reports and operational performance data for the parts. So new graph patterns and anti-patterns can be predicted by these AI machine learning algorithms. As I said, reviewed by human systems engineers, and then they can be added to the pattern library. So for the further generation and validation of the digital thread later. And once this curated library of graph patterns exists, it can be automatically applied to models and to data streams originating from various tools and repositories. So it can rapidly build the inter-model relationships that comprise the digital thread. That's what the steps A1 through A3 are. We're going back to the automated process where we just saw, but we're now using algorithms, formulas, graph patterns that have been generated by machine learning. So a graph pattern specifies the rules, essentially, as graphs. Two of the possible patterns that we might say are shown here. For example, every system requirement must be satisfied by a system element, say a structure, a function, and it must have a test case to verify the same. That might be a pattern that we have pulled out of the existing digital thread and that we want to have repeated in future work. Or pattern might be every system element must have an allocation to a hardware definition, like a part in a PLM or CAD system, and a software definition, such as code in GitHub or GitLab. So once we've developed these graph patterns and say, okay, they're valid, that's what we want, we can then apply those to the data through automated and scheduled custom scripts, first to identify missing or invalid relationships, and then to build new and updated intermodal relationships. So in this particular example, new intermodal relationships might be created between systems requirements in Doors Next Gen and SysML architecture elements in SysML Magic Draw, or tests in TestRail. Again, based on the application of this pattern shown here. And so, of course, this becomes iterative. The changes to the digital thread launch a new round of machine learning. Our goal overall here in this area is to be able to leverage the best new information technologies in areas like graph databases, DevOps, and machine learning, all in the service of systems engineering. So again, that's a little peek at the future. I think it's going to be important as we go forward in achieving this goal of seamless integration, seamless traceability. So I'm coming to the end of my time. Let me just end with a few concepts, hopefully that you'll take away from this talk. Well, first of all is that building the digital thread is an important issue. It's not something that ought to be overlooked in the excitement of what we're able to do with these digital threads. And it's very deeply entwined with your systems engineering process. Second is that there are multiple efficient approaches to building the digital thread, and that the community is still learning what works best. When you're evaluating digital thread platforms, look for infrastructure that doesn't lock you into a single workflow. And then finally, the long-term goal is to make the process as transparent, as seamless as possible, so that we can reserve human intervention for work that really requires sophisticated engineering judgment. Well, I do appreciate the time to talk tonight. We've really only touched on one part of this, what is a very big topic right now. How are we going to actually do modern digital engineering? If you would like to learn more about Syndea and the digital thread, here are a few resources for you. With that, I'll thank you for your attention. And I think we've still got a few minutes left for any questions.
Dr. Zwemer, thank you very much. Great presentation, very interesting. This is really an introduction to the whole field for me. By the way, this is Steve Beamer. I'm sorry, everybody. I did have a question, so let me start it off with the Syndea software. So I'm intrigued. Does the software actually call the various tools when it's trying to create these digital threads, say among two tools? In other words, if I'm creating threads between Doors and Cameo, for example, does your software, does it actually call those two tools, or does it simply manipulate the data sets that are associated with the two tools? I'm trying to understand the process.
No, it's an excellent question. The answer is yes. You actually talk to those individual repositories, the Doors repository, and for example, the Teamwork Cloud repository, so that one of the things the the Sadea platform provides, is a set of endpoints for each of those individual repositories. But rather than having to go through, all of those different interfaces individually, you can do them all through a single API. That is the Sadea Cloud REST API. So it gives you basically a single portal into all of these different repositories.
Excellent. I've had experience where I've had to take data sets, for example, a doors data set, and to try to link it to a SysML tool or model. And it's manual. That's what I've been doing for the last 30 years, is simply doing this manually, which of course is tedious and error prone. For one. So to have a mechanism to build those connections, those digital threads, and then to lay down and understand what I'll call the digital thread landscape between the different models, to me would just be fantastic. It would be a game changer.
Yeah, to be able to build that and to be able to build it so that it's, it's flexible, it's configuration managed, it takes into account the dynamic nature of the systems development process. I think that's one of the big challenges.
Exactly. And then to follow up on that, when you need to go in and make some changes to one set of models and to the data sets associated with those, having that automated created digital thread just helps immensely, because that's been a huge area which initially was helped a great deal by model-based systems engineering tools, but still a lot of it is done manually today. So when you start making changes to one part of the tool set, that you have the suite of tools, it was a nightmare trying to understand the ramifications, the impacts, and how those impacts propagate through the rest of your tool suite. So yeah, I'm sorry, I'm resonating with what you're talking about, because again, for a guy who's been doing a lot of this manually, this is great news for me. Oh, excellent. So I don't want to hog the Q&A though. So does anyone else have any questions?
Yeah.
Yeah,
Hey,
I had a
Steve.
quick one. Oh, sorry, Dave.
Oh, sorry, Clinton. I'll go real quick then. Clinton, hey, how
Okay.
you doing? Hey, it's Dave Fadley. Is there anything on your interface interaction between models? I guess you use an API. Is there any standard stuff that's open standard through that, or is that all proprietary?
In terms of the APIs themselves, each of the repositories, of course, has their own API. There's an enormous range. There are some that follow standards like OSLC. There are others that are purely native. We're pragmatic in terms of how we communicate with those individual repositories. But in terms of how we address them through our API, essentially we have to create a relatively simple data model, a simple ontology that's sufficiently broad that it can incorporate all of these different heterogeneous data sources. And that's been part of the challenge of doing that. How do you provide common ground to 30 different engineering tools, all of which have their own individual data models, their own individual APIs? Essentially trying to provide a single pane of glass to see all of that is really the challenge that we faced.
Yeah, absolutely. And do you know roughly how many different models you guys have designed to communicate with?
Right now, it's a little complicated to say that, because there's some that are kind of fully developed. I would say there's probably about 25 of those, but we can also provide access through kind of more generic interfaces to really, for example, anything that has a REST API, we have a way of being able to create connections to. And, you know, that opens up thousands of different repositories.
Right. All right. Thank you.
Hey, I had a quick question, Dr. Zwemer. Is like you talk about the integration of all these, disparate tool sets and stuff. And I was curious about like the sustainment and maintenance of that as these tool sets change versions and they modernize their own platforms over time. It's like, how frequently, does that impinge on those interconnections, the thread that break them, how robust is that, hold up to these tool sets in their, continual, changing and stuff like that?
Yeah, in general, we have not run into too many problems. Each of these tools are changing, some of them more often than others, but the API rules change, and that can make a difference. But in general, because we're mapping those individual elements, at the digital thread level into a common data model, really what it means is we just have to update, how we deal with the individual tools, our connection to the API, the kind of metadata that we carry over into the digital thread is not affected. Now, does that create a problem if the customer, the user is working with, for example, two different generations of Team Center?
Right.
And this is an issue we've dealt with very specifically. Then it does mean that you do have to be able to, if there are discrepancies between the data models that impact that, then you do have to essentially set up different categories of connections. But there's no reason that you can't have those, occurring, within the same digital thread.
Okay.
So, the answer is yes. The APIs of the individual tools do change. In general, however, we can minimize the change, at the digital thread level, and make it transparent to the user. But that's something we have to constantly do, is to make sure that we are updating our API accesses to those individual tools.
Gotcha. I think Dan O'Neill had a.
Yeah. Hey, sir, how you doing?
Good.
Go Jackets. I'm a Georgia Tech long ago kind of guy, and you live in Atlanta, so hopefully we got the same football team.
I wish they were doing better these days.
Yeah, they lose to Georgia, but I guess that's understandable because everybody does. Hey, my question is actually the other way. And I have to preface all this that I'm old Army, and Dave Holtz, you're online. So Dave is one of the smart APLers who machine learning and AI is coming soon. I actually come from the other way, old Army majors that are putting together requirements, start in Excel or Word in often very scripted, the system shall ... the, response must ... Would Syndeo be able to interact with Office tools so that we could kind of skip having to train the warfighters? We could just tell them, if you wrote this in Word, PowerPoint, or Excel, thusly, it'll tie together to everything we're trying to pull off. Over.
Yeah, we are doing some work along that. Some of the tools that can be part of the digital thread are Microsoft Excel, Confluence.
Yeah, and I guess I'm wanting to go one further, which is actually having observed ML AI emerge since 1993 when I went to grad school the other time. We're trying to find patterns, but we already know the pattern because at Defense Acquisition University, we teach the military officer the pattern that they're supposed to use. I think we could like own the algorithm in something like Excel and tell people, you know, cell A1, A2, A7, D59, and C99, you know, are the calculation of the thread. And people would be like, wow, you know, and they just update their stuff in Excel and stay there. And the fact that we're, you know, Beamer and Holtz are in a system model and in a Cameo model and a RecFi architecture, you know, we'd hide that from everybody. Am I making sense at all?
Oh no, I think this is one of the ongoing efforts within the systems engineering community, which is how do you input data into the model in a way in which a wide variety of users can do. And I think we've been part of some of those efforts because we can provide interfaces to a lot of different tools to be able to make that happen. Again, one of the efforts is called OpenMBE, which was set up originally as a way of being able to take people entering information in spreadsheets and be able to dump it into SysML modeling tools. Without the people having to know anything about SysML or Magic Draw or Rhapsody or any of the other tools. And so those kind of interfaces were created, and then we came along and said, well, it doesn't just have to be dedicated to SysML tool. You could use the same basic approach to be able to dump it into Doors, or to be able to dump it into TestRail or Jira or whatever tool that you're using to be able to capture that kind of information. So yeah, that's kind of, I think, a key effort that workers in the field do recognize, is that we need better ways of interacting with these very sophisticated engineering modeling tools, both in terms of inputting data and in terms of getting data out. And so
is there a standards body for, I'll call it SysML for dummies?
Not for SysML for dummies, as far as I know. Of course, the OMG is the standards body for SysML itself. And they're working very hard right now on SysML version 2, which is hopefully simplified. We'll keep our fingers crossed on whether it actually is simpler or not. But I think that's an interesting effort in terms of the specific goal that you mentioned. Is how can we, as I said, interact more efficiently with these sophisticated engineering tools, with less sophisticated users. I don't know if a single organization, I mentioned OpenMBE. The OpenMBE consortium is a collection of primarily users who've gotten together to figure out how to make that happen and how to adapt it in their own organizations.
Perfect. Hey, and just thank you for coming. We really appreciate. I know you're not physically up in Maryland, but we offer you a crab cake, virtually.
Well, thank you. I've got a favorite crab cake place over on the Eastern Shore, and next time I get there, I'll think of you guys.
Hey, we have one. We have time for really one more question. There's a question in the chat from John. He says, in building a complex system, you often don't want a user to have access to all info. Maybe you want them only to have access to things they need to know. Is there a way to handle this kind of compartmentalized security?
Yes, and it's a critical need in this area. When we talk about this idea, if you've got all these different data consumers, but not all of them are going to be authorized to see all of the individual data. So, how do you how do you protect that information? The good side is that each of those individual repositories, whether it's requirements or PLM or ALM, they have their own authentication mechanisms, their own authorization protocols. So your digital thread platform, has to know how to honor those. So, it may be that I can see kind of the top level digital thread, but I can't get into the underlying PLM information it's connected to because I'm not authorized to see that PLM bill of materials. So yes, that's the way it tends to be set up. Of course, there's a layer of authentication on top of the whole digital thread, which says, I have an account, it lets me see certain things. If I don't have an account, I don't see anything. If I do have an account, maybe I can see certain projects and not others. But yeah, that's a critical aspect of this, in a practical sense.
Sorry, can I ask one more question? This is Jenny from APL, working with Daniel together.
Yes, please go ahead.
Okay, so basically our group bought a license of Syndias. We're trying to, evaluate, work on that license. And, we're trying to, for example, test the Creo interface, also trying to Windchill. Looking at the compatibility, the most recent version 3.51 have been tested for Creo 7 and the Windchill 11 or something, but we have Creo 9 and also Windchill 12. So we have some kind of issues connecting, things. So I was wondering, what's the best way to get support from the Intercax?
Yeah, if I can go back to this particular thing here, the fourth one down here is our online help desk. If you go to intercax.com/help, it will direct you to set up an account. That's fine. You just go ahead and register, and then to submit your technical request. And then it will go right to our technical support team. They will farm that question out to the right expert to get those questions answered. That's by far the most efficient way of, getting the information to us, making sure that we're tracking it, that we're responding to it on schedule.
Okay. Yeah, we have one ticket like this. We have not got a response yet. So just trying to see how can we see it.
All right. Well, you're very welcome to email me. You can send it to info@intercax.com, and we'll escalate that. If you're not getting a response, then we'll look and figure out why not.
Okay. Thank you very much. Great presentation. Thank you.
Thank you.
Well, with that, we're going to wrap it up. Dr. Zwemer, thank you so much for a really interesting presentation. Obviously, by the strength of the questions asked and the fact that we're over our time limit, just shows how much we all appreciate you coming out and talking to us and presenting these ideas and your services. So please, on behalf of the Chesapeake chapter, thank you very much.
Well, again, thank you for the opportunity.
Excellent.